afternoon is Moshe Adrian from Queen's College, and he'll speak about a remark on the Kottwitz homomorphism.
Thank you, Vincent, and I also want to thank the organizers of the conference. It's been a wonderful conference so far.
There's a microphone.
I tried it. It's not quite working. This one. This.
Did you unmute it?
Did you put it on?
Hello? Oh, okay, great. Okay, so thank you again to the organizers. It's been a really wonderful conference. So what I want to talk about today is the Kottwitz homomorphism and a sort of small feature of the Kottwitz homomorphism that I've thought about over the past couple of years. I want to motivate this talk by the following sort of classical question, which has actually appeared in some recent works in the past couple of years, which is if you take a connected reductive algebraic group over a field, the natural question that many have asked is whether if you fix let's say it's a split group, if you fix a split maximal torus, does the Weil group have an embedding into G? And that's the same thing as asking if you take N, the normalizer of this maximal torus, and its projection to the Weil group, is there a splitting of this projection? And as I understand the answer to this question is not completely known, but I think for the almost simple split groups, the answer is known, maybe a little bit more generally than that. For a p-adic group, there's a simpler question than this one, which is if you take, so let G be split over p-adic field, T maximal split torus, and the simpler question that I'd like to talk about is if you take the normalizer, so N is the normalizer of this maximal split torus, there's a projection to this group omega, which I'll say a little bit more about, is the subgroup of the extended affine Weil group, which stabilizes a fundamental alcove in the building G. That was a lot of words, but I'll make things much simpler in a moment. So we have this projection. So here again, we have to be in a p-adic case. So the question is there a splitting of this homomorphism? And equivalently, is there a splitting of the Kottwitz homomorphism? So this map comes from, more generally, a map from G of F to omega, and this is the Kottwitz homomorphism. But we don't need this more general map. I'll just explain this map from the normalizer to omega. So what is this map from normalizer to omega? So we have our normalizer, maps to n mod the integral points of t. And normalizer modulo this integral points is isomorphic to the extended affine Weil group, which is given by co-character lattice of T, semi-direct, this finite Weil group. And then there's a projection to the extended affine Weil group modulo the affine Weil group. And the affine Weil group, so this is co-character lattice, semi-direct Weil group. The affine Weil group is the co-root lattice. semi-direct vial group. And this final quotient is omega, which what we have here is none other than x lower star modulo the coroot lattice. Isomorphic too, I should say. Okay. So this is the map that I'm interested in, and the question is whether there's a splitting of this map, of this projection map. Okay, so let me just I'll state the main result, and then I'll say, for the rest of the talk, I'll discuss how to achieve this result. Okay, so maybe I'll call this map kappa. That's the standard notation for the Kottwitz homomorphism. So the map, the hom kappa, gives some conditions. So let G be almost simple split. Then this map, kappa, splits. So in other words, there's a homomorphic section of that map. And moreover, I won't write it down, but I'll talk about it later. I'll exhibit an explicit section. So an explicit map from omega to the normalizer. Okay, so that's the main result. And let's see, is there a... So let me set up some background. Maybe what I want to say first is, in order to say what this section is, the first thing that I'd like to do is give a parameterization of omega. And then on the elements of omega, I'll give an explicit map on these elements. So the first thing that I need is a parameterization or a description of this omega. So you kind of forget about this other stuff that I've already talked about for now. Okay, so we're going to fix a set of simple roots a set of positive roots, let's say pi, simple roots, delta, so we give these names alpha 1 through alpha n, and I'm going to let alpha 0 be the highest root. And another ingredient that I need is are the fundamental co-weights, so let epsilon I be the fundamental co-weight associated to the root alpha sub I. So what does that mean? Just to remind you that epsilon I, comma, alpha j is 0 if j is not equal to I, and 1 if j equals I. So, fundamental co-weight. And in order to describe this group omega, I need to recall some final elements, so I'm going to recall W sub delta. This is going to be the longest element of the vial group, so more specifically, this is the element such that W delta squared is 1, and W delta of this simple system is negative delta. And if I let delta I be delta minus alpha I, okay, so I have a subsystem, and I let capital Wi be the group generated by S alpha 1 all the way up to S alpha I hat, so I'm removing S alpha I. This is a sub-Weil group. So these are simple reflections associated to simple roots. We also have an element W delta sub I. So this is W sub I, such that W delta sub I squared equals 1, and again W delta sub I is negative delta sub I. Okay. And, okay, so how do we describe omega? So a result from a paper of Iwahori Matsumoto says that so the group omega, or rather, I'll consider the omega for the adjoint group. So if G is, again, we're assuming G is almost simple. If you take the adjoint group, then the omega for the adjoint group is parameterized by the following 0, and the collection of fundamental coweights that have coefficient 1 in the highest root, in the expansion of the highest root in terms of simple roots. So actually the fundamental coeweights epsilon sub I, such that the associated simple root has coefficient 1. So in other words, the product of epsilon I in the highest root is equal to 1. And there's a bijection between this set and omega for the adjoint group. So this is from Iwahori Matsumoto, and the bijection says 0 to 1, and epsilon sub I, so here's why I needed these Weil elements, to so remember, omega is a quotient of the extended affine Weil group, and so we can consider those elements of omega as just tuples, co-character, comma, Weil elements. So the tuple is epsilon sub I, comma, W delta sub I, Wi. So that's the bijection. And I'll remark, this, we call it Wi, which is W delta sub I, W delta. This is an automorphism of the extended Dickin diagram. And I'll give some examples in a moment. So it's a familiar object. Okay. And the action of this Weil element on the extended Dickin diagram is explicitly written out in Iwahori Matsumoto, or I think Bourbaki, for the latter. Okay, and the action is, yeah.
So in this map, we want to write W delta I, W delta.
Yes.
You wrote WI.
What is the W?
Oh, did I write down? Sorry, W delta, thank you. Yeah. W delta I go, thank you. So maybe before I give some examples, we just say, what about omega sub g? Not necessarily the adjoint form. So, for a general, well, let's say, an almost simple g is given by a choice of a lattice, so lattice, which is going to be x lower star, between the co-weight lattice and the co-root lattice. And so then omega g, actually we sort of said this earlier anyway, so for general almost simple g, this is x lower star of t modulo co-root lattice, which is contained in omega adjoint, which is, I guess, p check modulo. So p check is the co-weight lattice. So if your almost simple g is given by this lattice, so x lower star t, you just take, in order to get the bijection for g, you just consider the fundamental co-weights in that list that are actually co-characters that live in this x lower star t for g. So that are co-characters for g. There, yeah, okay. Okay, so that's that. So examples. So first example, type Bn adjoint. So the extended Dickin diagram looks like this. So we attach the negative, we attach the highest root to the Dickin diagram, and 3, and that's 1 out of 10. So there's the extended Dickin diagram, and this, so in this case, omega adjoint is z mod 2, and this is given by 0 and epsilon, I guess, sub 1. Okay, that's the description of omega. So the parameterized by the fundamental co-weight associated to the simple root alpha 1 in this standard, these standard coordinates. And so this W1, this W delta I, W delta, where I equals 1, just is the order 2 automorphism that flips the two nodes. And I should say, yeah, okay, and fixes the rest. Okay. Dn odd. Dn and odd adjoint. So in this case, omega add is z mod 4, and it's given by 0 epsilon. So I should write down. I should draw the picture first. So alpha 1, negative alpha 0, alpha 2, alpha 3, alpha n minus 3, alpha n minus 2, alpha n minus 1, and alpha n. So then omega is given by 0, epsilon n, epsilon n squared, which is epsilon 1, and epsilon n cubed, which is epsilon n minus 1. So it's given by the co-weights associated to the nodes of the regular Dickin diagram. And what is the, so maybe I'll give what does the generator do? So W sub n corresponds to the generator of omega. So epsilon n generates, and Wn acts by, this can all be found in Iori Matsumoto. It sends negative alpha 0 to alpha n, which goes to alpha 1, which goes to alpha n minus 1, which goes to negative alpha 0 back then. And then alpha sub I, so the rest of the symbol roots, so alpha sub I goes to alpha n sub n minus I. Here I is between 2 and n minus 2. Okay. Okay. So, what is the map? So I want to write down what the map is. So we have, for G almost simple, we have this map from the normalizer to omega, which again comes from, it's just a restriction of the Kottwitz homomorphism to this normalizer group. That's all that this is. If you prefer thinking in some more fancier language. So what is this? I now want to describe what the section almost is, and I'll say why I mean almost. So now we can write down, now that I've described this omega group, we can write down really a canonical section which does what? Well, omega looks like pairs epsilon comma w. So I take an element of omega, which corresponds to some fundamental co-weight comma vile elements. And in order for this to be a section, I should, so I won't say much about this, but so I should evaluate fundamental co-weight at a uniformizer. Okay, that's not the important part. But now what about this vile element? So what about the vile element? What do we do with the vile element? So with the vile element we send to n sub 0 of w, where n sub 0 is the tits section. So this is sort of coming full circle at the beginning. Tits defined a section of the map and goes to W. So it's a section of this canonical projection, and I want to describe what that is in just a moment. So this is a section of this Kottwitz map, and I said this is almost the answer. Let me call this map iota. I say almost because this map iota turns out to not be a homomorphism in all cases. So it doesn't produce a homomorphic section of the Kottwitz homomorphism. It produces a homomorphic section in all cases except for some type A cases, and weirdly enough, type Dn adjoint where n is odd. Those are the two cases where this section is not homomorphic. But because the structure of omega is so simple, if G is one of these almost simple groups, we can sort of fudge things around to produce, we can alter this map slightly to produce a homomorphic section. So before I say anything about that, what is this tits section? Okay, so for each, let me just recall some things. For each root alpha, with the structure theory of G, we have a map U alpha from the field F, so an isomorphism from the field F to a unipotent, a closed unipotent subgroup these unipotent subgroups corresponding to roots in G, and such that if you take an element of the torus, T, and you conjugate U alpha of X with it, you get U alpha of T, X. This is for all T in capital T, X and F. And to define the tit section, I have to say another thing. So the U alpha, these maps, U alpha may be chosen in a very specific way so that if I consider the element N alpha, which is U alpha of 1, U negative alpha of negative 1, U alpha of 1. This element, this is a pretty, I guess, it's a well-known element in structure theory of a p-adic group. This element lies in the normalizer and has image. S sub alpha in the valve. And now I can say what the tits map is. Okay, so if you take an arbitrary file group element and write it in as an expression in simple reflections, let's say beta 1 as beta 2, all the way up to S beta, let's say L, then Titz's section is given by N sub 0 of W is just, so we lift each simple reflection to that specific element of the normalizer. So N sub beta 1, and sub beta 2, which is a reduced expression, all the way up to N sub beta L. And it turns out that this definition, I mean, this is a well-defined expression. It doesn't depend on the reduction of W in terms of simple reflections. So this is the tit section of the projection from earlier. Okay, so I should say this tits map comes up in lots of different ways. So we have this map. So this is a section of the map from N to omega, and as I said earlier, it's not completely generally a homomorphism. But since so now let's say something about the proof of main result. So since G is almost simple, the omega groups are quite simple as well. So omega is cyclic except for type Dn with n even. So even though this map iota is not a homomorphism, well, it's sufficient in order to write down a section sort of capitalizing on this iota map. In the case that G is also assuming G is not type Dn and even, which I'll deal with later, it suffices to check that if rho generates omega, so the generator of omega, then, so then let's say, and rho has order m, let's say, then iota of rho also has order m. Okay. And then our section is our homomorphic is just going to be rho to the j maps to iota of rho to the j. Now this is the same, as I said, iota is not necessarily homomorphism, but when it is, this is the same thing as the map iota, but in general, in these exceptional cases, this is slightly different, just a slight modification of this iota map. Okay, so I had to tweak things a little bit, and I'll say something about that later. Now, so in order to show that this iota of rho has order m, or order whatever, so we need a computation. So iota of rho is this epsilon of var pi tits lift of w. So we just compute the power of such a thing. So maybe I'll give rho, be more specific. So let's say rho is epsilon comma w. So if we take the nth power of this thing, let's rewrite this. This is epsilon of var pi, n0 of w, epsilon of var pi. And now I just want to write this in a particularly slightly clever way. See why. So n0 of w inverse n0 of w squared all the way up to n0 of, so we have some epsilons in the middle as well. n0 of w to the negative m plus 1, n0 of w to the m. So there's some epsilon and n0 terms in here. Okay. And simplifying this gives the following expression. This is epsilon plus w of epsilon plus w squared of epsilon all the way up to w to the m minus 1 of epsilon. This is evaluated at var pi. Times n0, the lift of w to the nth power. Okay, so we want to show that this expression is trivial, and so we sort of divide this computation into two parts. So we end up showing that each of these separate parts is trivial. So this this co-character, so epsilon plus w epsilon plus all the way up to w to the n minus 1 of epsilon is 0. And secondly, that the lift of w to the m, the order. So it turns out if rho has order m, then the w associated with rho also has order m. Okay. So this, I'll see that here. So remark, rho order m implies, so let's say rho equals epsilon w order m implies that w is order m. And so we show that this, I guess that's not necessarily, maybe that's not needed for this, but it's still a remark. Okay, so we show these two things. I won't say anything about the first. I mean, I won't say much about the first, except for the fact that the first is essentially a brute force computation. One can find in Bourbaki explicit expressions of these fundamental coweights in terms of as combinations of the simple roots, let's say. And then we know the actions of this element w on the simple roots, and so you can compute explicitly what the left-hand side is, and you go type by type, isogeny by isogeny, and check brute force that this sum equals 0 for all the g's. The second one is slightly more complicated. So,
sorry, what is W?
yeah, sorry.
What is W there? Which element?
W, so here, I wanted to show that if rho, so in order to show that the Kottwitz, this section has a splitting, well, I wrote down conjectural splitting, and it's given by, in terms of a generator of omega. To give it a splitting, I want to show where omega to the j goes for every j, where omega generates, rho, let me say that again. Omega is generated by rho. Omega is, so I'm only dealing with the cyclic case right now, so not type D, n, where n is even. So therefore, omega is cyclic. It's generated by some element rho, which can be written as epsilon comma w, a co-character comma a Weil group element. And my splitting sends rho to the j to iota. I wrote down iota earlier. Iota rho to the j. And I computed what iota rho to, so I said, it suffices to show that iota of rho to the m is trivial, where m is the order of rho. And we have this computation, and w, I guess this is the answer to your question, w is the Weil element associated to rho. And so we end up wanting to show these two things. Okay, for this second part, we need the following tool. So we have a formula, following formula for, did I use m already? Let's just use it again. I did use m. Let's say n0 of w to the k. So if you take the lift of any, so let's say u. Let u be an element of the Weil group, an arbitrary element of the Weil group. Then we have the following formula on the power of, an arbitrary power of the Titz lift of u. It's the following. It's n sub 0 of u to the k times the following product from I equals 1 to k minus 1 products over the set of positive roots alpha such that w to the I of alpha is negative, but w to the I plus 1 of alpha is positive. So it's a product over these positive roots. of alpha check of -1. That's an explicit formula for an arbitrary power of the tits lift of an arbitrary Weil element. And so, in our situation, we're checking about the mth power of m0 of w, and m is the order of rho, hence is also, by that remark, the order of w. And so, in particular, just a small thing, is that this first term vanishes. It's trivial, because in the case where we're considering this w with order m, and we compute the nth power of the tits lift, this first term is trivial, so we end up needing to consider this double product, and that computation is also a brute force computation. I go type by type, isogeny by isogeny, and compute this double product of these alpha checks of -1s, and I show that this is indeed trivial as well. Now, where does this formula come from? So I need to also say where this formula comes from, because where it comes from is used to tackle this other case, dn, where n is even. So this formula comes from the formula if u and v are arbitrary Weil elements, then we have a formula for the product of the lifts. So the product of the lifts is the lift of the product times some other products. This is some co-cycle type identity. So we product over the alpha, positive alpha, such that v of alpha is negative and u of v of alpha is positive. And again, we're taking the product of alpha check of -1. Okay. So this formula comes from Langland's Shellstead, paper of Langland's and Shellstead. And more recently, we can find this in Rostami. And so that's for arbitrary Weil elements, and so you can recover this power formula from this more general product formula.
Does one know exactly when the other term is 1?
Sorry?
Does one know exactly when the other term is 1?
When
The
which term is one? Sorry.
product.
If you, for u and v arbitrary, or I think that's, I would say that that's not known, and it's probably quite complicated. Maybe one, I'm not 100% sure, but perhaps in the almost simple case, one could maybe do a case-by-case examination of that question. But I don't know if there's a general formulation for when that product is one. I could be missing something.
Equivalently, when the tit section is a homomorphism.
Sorry?
Equivalently, when the tit section is a homomorphism.
Oh, sure. So if you're asking, if you're asking when is this product one for all u and v, then yes, that's equivalent to the tit section being a homomorphism. And for almost simple groups, I think one can say when, at least for almost simple groups, one can say when a tits lift is a homomorphism. And I think that's very rare, in fact. Now, that's kind of a separate question. So when is the tits lifting or the tits section a homomorphism? I think that's a very rare event. But that should be compared with the question, when can you find a homomorphic section of the map n to w? And that's, so So the comparison of these two questions is related to another ongoing project, which, yeah, it's a great question. Okay, so, okay. Okay, so I should say that 1 and 2 are proven by brute force computation. And I should, so, remark. The second remark is that for type dn and even, and let's say adjoint, I guess this is the only case where omega is not cyclic. Dn and even not adjoint, the omega groups are cyclic, but so this is really the only exceptional case. Don't think I said adjoint earlier when I was mentioning this, but that should have been said. In this case, we need the general product formula for the Titz lift. And it turns out that iota is a homomorphism. So the original iota is a homomorphism in this case. Third remark is that the original iota, so remember we modified this iota slightly in some bad cases. Iota is not a homomorphism so in some, I don't know exactly which, but at least some type AN cases, and DN adjoints, and on. And it comes down to the Titz lift. It's the Titz lift and 0 that causes problems. That map is not a homomorphism on the subgroup of the Weil group generated by this W, the W that's associated to a generator of omega. Okay. But in the end, this map that I wrote down, rho to the J goes to iota of rho to the J is a homomorphism. Okay. That's all I wanted to say. Thank you very much.
Are there any questions? Jessica?
Do you conjecture your result?
Sorry.
Do you conjecture your result? Also, if you are not assuming this result?
Yes, definitely. That's a reasonable, I think that's a totally reasonable conjecture. And what I want to say about it is that using the techniques from this talk, namely trying to write down an explicit section using the Titz lift and then modifying it in some dumb way, will not work. That will not work to generalize this result beyond almost simple groups. It pretty much very quickly causes huge difficulties. On the other hand, I can say a couple of things. As I was responding to Dependra's question, one thing that seems interesting is to sort of try to understand this comparison, or to try to understand the phenomenon of why the tits, the difference between the tits lift not giving a homomorphic section from the normalizer to W, and the fact that I guess many more groups have a homomorphic section, or an embedding of the file group into G. The tits lift not explaining that. So I guess another question is, what if one considered, instead of using the tits lift of the file group, maybe another lifting of the file group? And that's something that's in progress. And then on the other hand, again, talking with Moshe a few weeks ago about these things, seems Moshe has a very nice idea on how to generalize this result to an arbitrary group, following the original construction of Kottwitz, the Kottwitz homomorphism. So this is sort of not this proof really almost has nothing to do with the construction of the Kottwitz homomorphism. But if one goes back to the original construction, then it seems that there's a much more elegant and smooth proof for a general reductive group.
That was my first question as well. I have a second question. So, Jean Stani told me that his work, I guess it's the one you mentioned on the blackboard, was motivated by trying to understand how to describe the inducing data for simple supercustomers. Is there some motivation like this for your talk as well?
I have zero motivation for this work. It was a question that was asked to me of my former office mate in Toronto. I was debating whether to share this, what I find to be a slightly funny story. I might as well just share it since it comes up. So my former office mate asked me this question, which is, if you take this omega group, stabilizer of fundamental alcove, does it embed into your p-adic group G? He asked me that a few months after arriving to Toronto, and I had absolutely no idea. I mean, I had at that time zero hope of understanding anything. And a few months later, he asked me the same exact question as if he had never asked me in the first place. Oh, by the way, I'm wondering, do you have any idea about this question? And I still had no idea, so I responded, I have no idea. A few months later, as if he had never asked this question 2 times, he asked me again, and again I had absolutely no idea. I finished my postdoc in Toronto, left, started at Queen's College, and a few months into my beginning at Queen's College, I get an email again from him, written as if he had never asked this question. And I decided at that time that maybe I'll give, instead of 30 seconds of thought, I'll spend 5 to 10 minutes thinking about the question. And finally, after the 4th time, I had a small idea which eventually turned into this paper. So if there's a moral of that story, maybe it should be that if you have a question, ask it multiple times to the same person. Zero motivation, except for,
See the minimum number? As it's 4?
it was 4 times. I counted it as 4 times.
Any other questions? So let's